Buckle up, it's space-time. Number 10, the fine-tuning problem. In 1979, Cambridge University physicist Martin Rees sat down and began calculating what the universe would look like if its fundamental constants were even slightly different. The results were not reassuring. What he found, and later published in his landmark 1999 work Just Six Numbers, was a portrait of a cosmos balanced on the edge of a razor, where the difference between everything and nothing was a matter of decimal places. The universe runs on 6 fundamental numbers. These constants govern the strength of gravity, the behavior of nuclear forces, the geometry of space, and the expansion of the cosmos itself. Scientists had always assumed these numbers were simply what they were, fixed properties of reality, no different from the rules of a game. Nobody asked why the rules were those particular rules. Then Rees began adjusting them. If the strong nuclear force were just 2% stronger, hydrogen would never have formed in the first place. No hydrogen means no stars, no water, no chemistry, no biology. If gravity were even fractionally more powerful, stars would burn through their fuel in thousands of years, rather than billions, extinguishing long before any orbiting planet could develop life. The constants are not merely convenient. They appear precisely calibrated. What makes this genuinely unsettling is that these numbers cannot be derived from any deeper theory. Physicists cannot calculate what they should be from first principles. They simply are what they are. The cosmological constant, which governs the expansion of space, is fine-tuned to a precision that staggers even the most seasoned theorists. No known law of physics explains why any of these values landed where they did. The universe did not have to be this way. It could have been any of an essentially infinite number of other configurations, almost all of which produce nothing, and yet, here we are in the one version that works. Number 9, the matter-antimatter asymmetry. At the moment of the Big Bang, the laws of physics, as we understand them, required that matter and antimatter be created in exactly equal amounts. This is not a debatable point. It is a direct prediction of the standard model of particle physics, the most precisely tested theory in the history of science. Equal matter and antimatter means total mutual annihilation. Total annihilation means the universe produces nothing but radiation. No atoms, no galaxies, no anything. For decades, physicists assumed the symmetry must have broken somehow, that a process called CP violation, a subtle imbalance in the behavior of certain particles, had tipped the scales. In 1964, James Cronin and Val Fitch at Brookhaven National Laboratory observed CP violation experimentally for the first time, a discovery so significant it earned them the Nobel Prize in Physics in 1980. Finally, it seemed, there was a mechanism that could explain our existence. There was one problem. The degree of CP violation that Cronin and Fitch measured, and that all subsequent experiments have confirmed, is far too small. The known asymmetry in the standard model accounts for only a tiny fraction of the matter, surplus that would have been needed to produce a universe like ours. The mathematics simply does not balance. For every billion antimatter particles produced at the Big Bang, approximately 1,000,000,001 matter particles were created alongside them. That single surplus particle per billion is the entire observable universe. Physicists know that additional sources of CP violation must exist beyond what the standard model describes. Experiments at CERN and at the KEK laboratory in Japan have spent decades searching for them. So far, the full answer remains out of reach. If the universe was built on perfect symmetry, something broke it. We do not know what. And without that break, we would not be here to ask. Number 8, the origin of life's chemistry. On a spring morning in 1953, graduate student Stanley Miller arrived at his laboratory at the University of Chicago and switched on an experiment that would make headlines around the world. Working under Nobel laureate Harold Urey, Miller had constructed a sealed glass apparatus filled with gases thought to represent the atmosphere of early Earth: methane, ammonia, hydrogen, and water vapor. He ran electrical sparks through the mixture to simulate lightning. Within a week, the water in the flask had turned a rich reddish brown. Miller had produced amino acids, the molecular building blocks of proteins. The origin of life, it seemed, was just a matter of chemistry. 70 years of experiments later, that celebration looks premature. Amino acids are not life. They are components, like individual letters of an alphabet. To get from amino acids to life, you need self-replicating molecules capable of storing and transmitting information. The leading candidate is RNA. In 1986, Nobel laureate Walter Gilbert proposed the RNA world hypothesis, suggesting that RNA molecules capable of copying themselves may have been the original engines of life. It was an elegant idea. The difficulty is that no one has ever managed to produce a functional, self-replicating RNA strand from raw chemistry under plausible early Earth conditions. The gap between a flask of organic chemicals and the first living cell involves a sequence of molecular events of staggering improbability. Some origin of life researchers estimate the odds of a functional RNA strand assembling by chance at less than 1 in 10 to the power of 40. Others place the figure even lower. What makes this more puzzling, not less, is that life appeared on Earth surprisingly quickly. The planet formed roughly 4.5 billion years ago, and evidence of microbial life dates to approximately 4 billion years ago, within the first geological instant of Earth's history. The speed of life's emergence suggests either that the process is somehow easier than the chemistry implies, or that we are missing something fundamental about how it works. Laboratory experiments can produce the ingredients. No experiment has produced the recipe. After 7 decades of trying, the step from chemistry to life remains the most stubborn gap in all of science, and every attempt to close it reveals new layers of complexity we did not know were there. Number 7. The Cambrian explosion. For nearly 3 billion years, life on Earth was invisible to the naked eye. The oceans harbored single-celled organisms, simple films of bacteria, and occasional mats of microbial life clinging to the seafloor. The planet was alive technically, but featureless in any biological sense that a human would recognize. Then, approximately 538.8 million years ago, according to the current International Commission on Stratigraphy timescale, something changed. In geological terms, it changed instantaneously. In 1909, paleontologist Charles Doolittle Walcott was working in the mountains of British Columbia, Canada, when he discovered a layer of rock that would become one of the most studied fossil sites on Earth. The Burgess Shale contained the preserved remains of creatures from what scientists now call the Cambrian explosion, a period of roughly 20 million years during which almost every major animal body plan that has ever existed appeared in the fossil record simultaneously. Eyes, limbs, shells, nervous systems, predators, prey, the entire architecture of complex animal life materializing from essentially nothing. What makes the Cambrian explosion so scientifically significant is that it strains the standard Darwinian model of gradual change. Evolution is supposed to be slow, incremental, and continuous, a long chain of small modifications accumulating over vast timescales. The Cambrian explosion is not that. The fossil record shows no extended period of transitional forms leading up to it. Complexity does not build gradually. It arrives. The candidate triggers are numerous and contested. A rise in atmospheric oxygen, the thawing of a global ice age known as Snowball Earth, an ecological cascade effect, or some combination of factors that researchers have not yet fully untangled. What none of the proposed explanations satisfactorily addresses is the sheer informational leap involved. Building an eye, a jointed limb, or a bilateral nervous system from scratch requires not just raw materials, but coordinated genetic instructions of enormous complexity. The Cambrian explosion implies that this information appeared and was successfully assembled in a geological eye blink. 3 billion years of nothing, then every body plan that would ever exist appearing in a geological instant. Whatever hit the reset button on biological complexity has not yet been found in any fossil bed on Earth. Number 6. The Great Oxygenation Event and the Oxygen Window. Approximately 2.4 billion years ago, a group of microorganisms called cyanobacteria began doing something no living thing had done before. They started using sunlight to split water molecules and release oxygen as a byproduct. For the vast majority of life on Earth at the time, obligate anaerobes that had never encountered free oxygen in their environment, this was a catastrophe. The Great Oxygenation Event, as geologists call it, was the largest mass extinction in planetary history, triggered not by an asteroid or a supervolcano, but by the metabolic waste product of a microscopic organism. The survivors adapted. Over hundreds of millions of years, the oxygen content of Earth's atmosphere climbed from near zero to the levels that make complex animal life possible. Today, the atmosphere is 20.9% oxygen. That number is more significant than it sounds. Research by Earth System Scientists Tim Lenton and Andrew Watson, published in 2000 and subsequently refined, identified what amounts to a narrow biological corridor. Below approximately 15% atmospheric oxygen, fires cannot sustain themselves, and the energy available for large metabolically active animals drops precipitously. Above approximately 25%, vegetation becomes so combustible that sustained fires would ravage terrestrial ecosystems continuously, preventing the development of stable land environments. The window between those two thresholds is narrow, and Earth has remained inside it for hundreds of millions of years. What is not fully understood is how. The carbon-silicate cycle, biological productivity, and weathering processes interact to regulate atmospheric composition. But the precise mechanisms that have kept oxygen within the habitable corridor for long enough to produce intelligent life are still an active area of research in Earth system science. The system has wobbled. During the Carboniferous period, roughly 300 million years ago, oxygen levels rose to around 35%, and there is evidence of widespread fire. It came back down. The air you are breathing right now is the product of a 2.4 billion year balancing act, initiated by a microorganism that had no intention of making the planet habitable for anything larger than itself, and sustained by planetary feedback systems we are still mapping. It had no reason to succeed. Somehow it did. Number 5. The Moon's improbable role. By the standards of the solar system, Earth's moon is an anomaly. Most moons are small relative to their parent planets, captured remnants of the early solar system locked into orbit by gravity. Earth's moon is roughly 1/4 the diameter of Earth itself, a ratio so large that some astronomers classify the Earth-Moon system as a double planet. Its presence is not subtle. It is the most conspicuous object in the night sky, and it has shaped everything from Earth's ocean tides to the length of the day. What is less commonly known is how close it came to never existing at all, and what that would have meant for us. The leading explanation for the moon's origin is the giant impact hypothesis. Approximately 4.5 billion years ago, a Mars-sized body that scientists have named Theia collided with the proto-Earth in a glancing blow of extraordinary violence. The debris from that impact coalesced in orbit and gradually formed the moon. The hypothesis is supported by isotopic analysis of lunar rocks returned by Apollo missions, and it is now the consensus view in planetary science. It is also, by any reasonable assessment, a spectacularly unlikely chain of events. In 1993, French astronomer Jacques Lascar and colleagues published modeling work in the journal Nature, demonstrating that the moon plays a critical role in stabilizing Earth's axial tilt. Earth currently rotates at an obliquity of approximately 23.5 degrees, producing the regular moderate seasons that characterize our climate. Lascar's models showed that without the gravitational steadying effect of a large moon, Earth's axial tilt could vary chaotically over geological timescales, producing climate swings severe enough to periodically sterilize the surface. Mars, which lacks a large stabilizing moon, does experience significant chaotic variation in its axial tilt over millions of years. Remove the moon and the tides vanish, taking with them the coastal environments many biologists believe were critical transition zones for life moving from ocean to land. Remove the moon and the climate becomes a slot machine, pulling the lever every few million years and occasionally landing on catastrophe. A near impossible collision 4.5 billion years ago created the only thing that may have kept this planet stable long enough for intelligence to develop. Whether that is coincidence or something stranger, science has not yet decided. Number 4. The rare earth hypothesis. In the year 2000, University of Washington paleontologist Peter Ward and astronomer Joe Brownlee published a book with a quietly devastating title, Rare Earth: Why Complex Life is Uncommon in the Universe. Their argument was not dramatic. It was methodical, patient, and cumulative. They assembled a checklist of conditions that Earth meets and that complex life apparently requires, and they noted item by item how unlikely each one is to be found elsewhere. By the end of the list, the probability of any planet meeting all conditions simultaneously had become essentially impossible to state without scientific notation. The conditions begin with geography. Earth sits in what astrophysicists call the galactic habitable zone, far enough from the dense radiation-saturated galactic center to avoid sterilizing bursts of energy, but close enough to the zone of active stellar formation to have inherited the heavy elements needed for rocky planets and biochemistry. Our sun is a G-type star, stable and long-lived. neither too hot to be brief nor too dim to be energetically sufficient. Earth orbits within the stellar habitable zone for liquid water. Plate tectonics, a geological process not confirmed on any other rocky planet in our solar system, regulates the carbon dioxide content of the atmosphere and acts as a planetary thermostat over millions of years. Then there is the outer solar system. Many scientists believe Jupiter's immense gravitational field plays a shielding role, deflecting a significant proportion of long-period comets and asteroids that would otherwise pepper the inner solar system. The debate about the precise magnitude of this effect continues in the literature, but the general principle that a large outer gas giant reduces the bombardment rate of inner planets has substantial support. Remove Jupiter, and the impact rate on Earth may be dramatically higher. Each condition on Ward and Brownlee's list has some probability of being met on any given planet. The problem is that every condition must be met simultaneously, in the same place, and must remain stable for billions of years. The multiplication of those individual probabilities produces a number that approaches zero in any finite galaxy. Ward and Brownlee did not argue that we were lucky. They argued that the word lucky is not large enough for what we are. Number 3. The Fermi Paradox and the Great Filter. In the summer of 1950, physicist Enrico Fermi sat down to lunch with colleagues at Los Alamos National Laboratory in New Mexico and, during a casual conversation about flying saucers, asked a question that has haunted science ever since. The universe is approximately 13.8 billion years old. It contains an estimated 100 to 400 billion stars in the Milky Way alone, and a 2016 study led by Christopher Consulis at the University of Nottingham estimated roughly 2 trillion galaxies in the observable universe. Given those numbers and the apparent chemical universality of the building blocks of life, technological civilizations should be abundant. They should have had hundreds of millions of years to spread across the galaxy. So, Fermi asked, where is everyone? In 1998, economist Robin Hanson published a paper formalizing what he called the Great Filter. The argument is elegant and deeply troubling. Between the formation of a star and the emergence of a spacefaring interstellar civilization, there are many steps. Some of these steps may be extraordinarily improbable. The filter is the name for whichever step is so unlikely that almost nothing gets through it. The critical question, the one that keeps some researchers awake at night, is whether the filter lies behind us or ahead of us. If the filter is behind us, if the hard step was something like the origin of life, or the Cambrian explosion, or the emergence of human-level intelligence, then we may be among the first complex intelligences in the galaxy. Our apparent solitude is the prize we won by surviving a cosmic lottery that almost no one else has. That is the optimistic reading. The alternative is far less comfortable. If the filter lies ahead of us, then it is waiting for every civilization that reaches our level of development. Something systematically destroys technological civilizations before they become detectable at interstellar distances. After decades of operation, the SETI Institute has not confirmed a single extraterrestrial signal. The silence is total. The universe has had billions of years to fill itself with voices, and we hear nothing. Either we are something close to miraculous, or what happens next to civilizations like ours is something none of them have survived to report. Number 2, the anthropic coincidence and the universe's age. The universe has a lifespan, and it is not infinite. Stars form from collapsing clouds of gas, burn through their nuclear fuel across millions or billions of years, and then die. Stellar physicists have mapped this entire arc, from the formation of the first stars after the Big Bang to the slow, cold darkness that will eventually dominate when the last stellar embers cool and go out. The universe's active, starlit era, what astrophysicists Fred Adams and Gregory Laughlin named the stelliferous era in their 1999 book, The 5 Ages of the Universe, spans from roughly 1 million years after the Big Bang to approximately 10 trillion years in the future. After that, stars cease to form, and the lights go out one by one. We exist within that window, but not just anywhere within it. Data from the European Space Agency's Planck satellite, published in 2013, established the age of the universe at approximately 13.8 billion years. The first generation of stars contained almost no heavy elements. Carbon, oxygen, nitrogen, iron, all the chemistry that biology requires, had to be forged in stellar cores and scattered by supernova. That process takes generations of stars, each living and dying over billions of years. We could not have existed much earlier because the materials were not yet there. We also live in a period of relative cosmic calm. The early universe was a violent environment, saturated with gamma-ray bursts, collisions, and gravitational chaos. The era of galaxy formation was turbulent and often lethal to the prospects of planetary stability. Conversely, in the far future, star formation rates are already declining. The universe peaked in star formation approximately 10 billion years after the Big Bang, according to studies published by the Candles survey team. We are living in the long, gradual afternoon of that peak. The conditions for our existence are not just spatial, they are temporal. We required a universe old enough to have cooked the periodic table, but not so old that the stellar engines powering planetary systems were already burning out. The window in cosmic time that fits those requirements is real. It is measurable, and we are inside it. We did not choose when to exist. We exist in the only era we could have, which means the universe had to wait 13.8 billion years, arrange every prior event correctly, and hold itself together long enough for intelligence to become possible. Something even more fundamental than timing made all of that possible, and it is the deepest unsolved problem in all of physics. Number 1. The vacuum catastrophe. In 1917, Albert Einstein added a term to his field equations of general relativity. He called it the cosmological constant, a value he inserted to balance the equations and prevent the universe from collapsing under its own gravity. When Edwin Hubble's 1929 observations showed that the universe was expanding rather than static, Einstein reportedly called the cosmological constant his greatest blunder and removed it. Decades later, in 1998, astronomers Saul Perlmutter, Brian Schmidt, and Martin Rees, working with the High Z Supernova Search Team and the Supernova Cosmology Project, discovered that the universe's expansion was not merely continuing, but accelerating. The cosmological constant was real after all. Perlmutter, Schmidt, and Rees received the Nobel Prize in Physics in 2011. The constant's reappearance raised a question that physicists had been quietly avoiding: quantum field theory, the framework that describes the behavior of subatomic particles and is the most experimentally successful theory in the history of science, makes a prediction about the energy density of empty space. It predicts that the vacuum, the apparent nothingness between particles, should be seething with quantum activity, and that this activity should contribute an enormous energy to the cosmological constant. When theorists calculate the predicted value from first principles and compare it to the observed value, the discrepancy is approximately 10 to the power of 120. That is a 1 followed by 120 zeros. Physicists and cosmologists routinely describe it as the worst prediction in the history of science. This is not a rounding error. This is not a missing decimal place. This is a mismatch between theory and reality so vast that it has no parallel in any other field of human knowledge, and its implications are staggering. If the vacuum energy were anywhere near the predicted value, space itself would be expanding with such ferocity that no particle could ever come close enough to another particle to form so much as a hydrogen atom. There would be no chemistry, no matter, no structure of any kind, just an expanding void tearing itself apart faster than anything could form. The observed cosmological constant is almost nothing. By the calculation of quantum field theory, it should be almost everything. The difference between those two values is what made galaxies possible, what made stars possible, what made you possible. No physical principle, no symmetry, no theoretical framework yet devised explains why the vacuum energy sits at the value it does, instead of the catastrophically larger value that every equation suggests it should have. This is known as the vacuum catastrophe, and it is unsolved. Every star you have ever seen, every ocean, every atom in your body, every thought in your mind exists because a number that the laws of physics insist should be unimaginably large turned out to be, for reasons no one can explain, almost exactly zero. The universe should not have survived its own first moments. By every calculation we can make, existence itself was impossible, and yet here we are, improbable beyond all measure, in a cosmos that had no business being here, asking why. If you want to see more videos like this, click the video on screen now and make sure to subscribe.